All right, let's get started. It's my absolute pleasure to welcome Jack Harris to Toronto. Jack is a professor at Yale, where I first met him when I got there in 2005. Um, I have learned a lot from Jack over the years, starting from 2005 when I was a student in his graduate quantum mechanics course, right up until my PhD defense, where he taught me how to think about something which I thought I understood really well. So it's for at least that reason that I'm very happy that he's here, because I'm sure he'll tell us super exciting things about things we think we understand, which are harmonic oscillators. So bit of background about Jack. Jack got his PhD from UC Santa Barbara and then did a postdoc at Harvard, followed by a position at Yale starting in 2004. And then since then, his group has pioneered the field of quantum optomechanics and lots of variations of it to measure all kinds of fun stuff. One of my favorites is his measurements showing that you can get persistent currents even in plain old normal metals. And when I first learned about it, it was super exciting. Anyway, Jack always has very interesting things to tell us about things which may seem very simple. And so I'll pass it on to him to tell us the rest of the story. Thank you, Jack.
Yeah, thank you, Amar. So first of all, thank you very much for the invitation. It's a pleasure to be here in Toronto and at the U of T. I guess for some reason, my advancer is not working, so I'm just going to try and stay here by the laptop. Yeah, it's fun to be here, and it is fun to be telling you this particular story. And that is because this is not really a story about my main field. Like if I work in condensed matter or atomic physics, this is neither of those. And it's also not astrophysics, and it's not particle physics, and it's not biophysics. Really what I'm going to be telling you about is a story in mathematical physics, which is weird because I'm an experimentalist and not like any kind of math-oriented person. But the story that I'll be telling you about has to do with a kind of math that just as physicists, we all use all the time. So just to see whether or not that claim is valid, raise your hand if from time to time in the course of your work, you have to find the eigenvalues of a 2x2 or 3x3 matrix. Okay, good. So you are my audience. We are all sort of mathematical physicists in the same way. So that's the story that I'm going to be telling you about. And if you only take away one thing, it has to do with the fact that the degeneracies of such systems generally live on very interesting shapes, like knots and trefoils, and that their spectra generally have structures like braids and stuff in them. So everything that I'll tell you about, I understood thanks to my theory collaborator, Nick Reed, and his student, Judith Huller, who played a crucial role in all of this. At the end, I'll be telling you about experiments that were led by research scientist Yogesh Patil. So thanks to them, graduate students, and of course, our funding sources. So I'm going to tell you this story, not how it really happened, but I'm going to try and give an introduction that is about sort of where it ended up. And that has to do with a mathematical, oops, wow, it's really not. Okay, good, there we go. Yes, okay. So this is let me just tell you a mathematical curiosity that turns out to have big physical consequences. Real tangible physical consequences. If you consider polynomials of increasing order, second, third, fourth, fifth, there is a very dramatic transition that their solutions undergo as a function of order. So if you start, just to be clear what I'm talking about, this is a first order polynomial. The unknown is lambda, and I know how to solve this equation. The solution is minus a. I think squirrels can probably solve this. Like I bet if a squirrel has like a big pile of acorns and the acorns are getting eaten and it's not spring yet, they know sort of if they're in trouble or not. So I'm pretty sure squirrels know how to solve this. This is the second order version, which was solved in Babylonian times, as I understand it. And here's the expression for the solution in terms of these coefficients. You notice there's a square root and a plus or minus because it will turn out that for an nth order polynomial, there are in general n roots. So there's a plus or minus here. If you go to the third order, it was sort of in the Renaissance, I think, that this was puzzled out analytically. And it's another formula. It's a little bit too big to write here, but it involves cube roots and square roots and plus and minus and blah, blah, blah. Fourth order was solved a little bit later and involves exactly the same operations. It's a bit longer expression, but there it is. Fifth order wasn't solved analytically until the 19th century, and it involves special functions like hypergeometric functions or elliptic integrals and the like. Same thing at sixth order. There are sort of special functions and weird combinations that you can use. Seventh order, eighth order, so on and so forth. So no surprises there. For an nth order solution, there are n roots, and there's some nice complex analytic function that gives you those roots. Where's the dramatic transition? So if I were to look at this and I was just to sort of eyeball, well, where does something sort of striking happen? I would say it's right here. And this is extremely famous amongst mathematicians. For orders 5 and up, there are no solutions in terms of radicals. And this is kind of where Galois theory comes from. Lots of beautiful math. And as far as I know, no consequences for physics whatsoever for the physical world. As far as, if you know different, please let me know, because I'm super interested. But it does not fall into this category. There are no physical consequences of this. Okay, if you're a real aficionado of polynomials and their roots, you might be aware that orders of 8 and up play a crucial role in one of Hilbert's famous problems in the Kolmogorov-Arnold theorem. Also very interesting math. No physical consequences that I know of. The dramatic transition that I'm going to tell you about happens here. And it's not necessarily obvious from these expressions, but it is in fact the case that for orders 3 and above, the roots of these polynomials just naturally have cool structures like knots and braids in them. And yeah, and so that's the story that I'm going to be telling you about. And the reason that I would claim it has physical consequences, and so that there's an arrow taking you just beyond math into physics, is that in the real world, if you have a system of n oscillators, just classical, masses on springs, linear everything, nothing fancy whatsoever, the resonant frequencies of that system are precisely the roots of an nth order polynomial. Okay, so if I have this, 2 masses, 3 springs, or maybe generalized notions of springs, but still linear objects, or 3, the resonant frequencies of this will be the roots of a 3rd order or 4th order or 5th order polynomial in absolute generality. And the reason for this is that this very sophisticated equation here, F equals ma, for linear couplings, it can be rewritten this way, where the coordinates of all your objects are combined into some kind of vector, and the momenta are combined into that vector as the imaginary parts of the entries. Then the time evolution is generated by some matrix D. And so this is the n by n matrix. And this matrix is very easy to figure out what its elements are. It's just some combinations of these masses and springs. The eigenvalues of this matrix are precisely the resonance frequencies. And of course, if you want to calculate eigenvalues, probably what you are going to end up doing is to calculate the roots of the characteristic polynomial. This is it. This is my entire talk, and this is everything that I'm going to be telling you about. There's nothing really in addition beyond this. Okay? So, and the exciting thing, this is maybe going to be a very boring talk, but the part of it that is going to be exciting is that I'm going to explain to you a bit sort of why it is that systems like this have no interesting topological structure and systems like this do. Caveat at this point, all this nice, pretty math really only applies if we're sort of thinking about complex numbers. All this story holds if I'm taking these coefficients to be complex and I'm taking their roots to be complex. And it's not immediately obvious that that is then going to translate into physical reality, where that may not be relevant. So is this nice story still relevant to physics in the way that I've laid out here? The answer is yes, it is. And let me explain to you what I mean by that. And this will amount to a very short introduction to what's known as non-Hermitian physics or non-Hermitian systems. Basically, this is an equation that we encounter a lot in physics. In fact, you can tell it's super important because it doesn't even have a name. That's how important it is. It's so ubiquitous. If you're doing quantum mechanics of closed systems, this is the time-dependent Schrodinger equation for the state vector. Okay? If you're doing classical mechanics, this is F equals ma for n classical oscillators. Okay, if you're doing circuits, this is Kirchhoff's law. If you're doing sort of any kind of waves or whatever, if you're doing open quantum system, this is the Lindblad equation for a density matrix. This is just a thing that we bump into a lot in physics. And there are some scenarios in which this matrix of interest here is strictly Hermitian. and will only have real eigenvalues. If that's the case, which is for here, I have nothing to tell you. Everything you know, and I don't have anything to add to that. But in all these other cases, there's absolutely no reason for this matrix to be Hermitian or for its eigenvalues to be real. We live in a world with dissipation. Okay? And basically, this is maybe also the main point of my talk, is that if you're used to thinking about this equation in this kind of context with Hermitian matrices and stuff, there are a lot of big surprises in store for you. Okay. So what are some of the surprises? Eigenvalues will be complex. Perturbation theory breaks down. Eigenvectors aren't orthogonal. These are just the properties of a matrix that at least I was not used to thinking about. If you then think about the time evolution that's described by this equation, there's all kinds of crazy things. There's no notion of adiabaticity. Geometric phases and the like are totally different. You can get non-reciprocal time evolution and the like. This is a lot of things to talk about. I'm just going to be talking about this one feature here. Though in the 2 or 3 hour version of this talk, I would also tell you about some measurements of geometric phases and the like. So it's important, I think, to get familiar with these features, qualitative features that are different in this equation, because it just comes up in a million places. As you can see here, there are a lot of physical domains where we think about this equation, and there are a lot of applications that we put it to where there's no particular guarantee that that matrix will be Hermitian in nature. Okay, so that's the setup. That's where we're headed. If this is the physical system that we're going to be thinking about, it becomes this equation in F equals ma, where the time evolution is generated by this matrix. Again, if your system is lossless and reciprocal, i.e. if these linear couplings are just masses and springs, or electrically capacitors and inductors, then this matrix will be Hermitian, and all the linear algebra that you learned in quantum mechanics applies just directly. But in the real world, there are other linear elements as well. So in the mechanical world, this would be viscous damping and a non-reciprocal force like the Coriolis or Lorentz force. Electrically, they're equivalent elements like that. If this is what you build your network out of, then this matrix can be anything. There's absolutely no restrictions to its symmetry or anything like that, just naturally within the context of classical physics. Having then written out what all these matrix elements are, if you want to find its spectrum, that's the roots of the characteristic polynomial. These 9 matrix elements will, in some combination or another, determine the 3 coefficients of the polynomial. Okay? And in general, again, if you're sort of working with arbitrary linear elements, these can be any complex number. There's no constraints on them whatsoever. And if you are going to tune such a system, basically what you're doing, even if what you have knobs on are these physical elements which alter these matrix elements, really in practice, you can think of that. They only matter if they tune these coefficients. Okay. So our central question then is, what do the roots of a polynomial do as you vary that polynomial's coefficients? So in order to tell that story, again, here's the nth order polynomial that we imagine. It is specified by n complex numbers. Actually, we're going to mostly be able to get rid of the trace of the matrix because it doesn't do anything terribly interesting, which reduces by 1 the number of coefficients. And I'm now going to draw you a picture of all of this. Okay? This has been a little bit abstract. So one way of saying it is that these polynomials corresponds to just a simple Euclidean space whose dimension is given by twice the number of complex coefficients here. 2 real numbers for every complex number. So there's some space of this dimension in which every point is some polynomial, and where every polynomial of that order is a point in this space. This is a useful picture to have. There's another picture that goes along with it, which is that if you give me a point in this space, and hence a polynomial, that also specifies its roots. It's n points in the complex plane that are the roots of this polynomial. So there's a one-to-one correspondence between a point in this plane, a polynomial, and sorry, not a point in this space, the polynomial it specifies, and the endpoints in the complex plane that are its roots. Okay, so now let me tell you some fun facts. Those were not fun facts. The fun fact is that if I think about one particular polynomial in particular, like the one here, and then ask what happens to its roots when I consider other polynomials that are nearby and connected to the original one by some little path. As I move around this path, what do these roots do? So here it is in PowerPoint animation. We'll do that again because that was a lot of work. So if I do that, what do these four roots do? Like, they're going to move around, they're going to change. I can tell you a few things right off the bat. Just common sense tells you that the spectrum of roots at the start of this loop is exactly the same as at the end, because it's exactly the same polynomial I'm considering. There are also some nice theorems that tell me that these roots will only move around smoothly as a function of these changes here. They won't do anything super exotic. And so if this loop is very, very small, I can also then conclude that none of these roots are going to change very much as I go around this loop. But each one will sort of wobble a little bit and then come back to itself. If that's the case, though, everything that I told you allows for the, so if I change that small loop by a little bit, the trace of these eigenvalues will change a little bit. But if I consider a much different loop, like a loop that goes crazy, these roots can go arbitrarily far away. And everything that I told you still admits the possibility that the spectrum starts out like this, it ends up like this, it's smoothly connected one to the other, but it may be smoothly connected with the eigenvalues intermediate evolution doing something like this. If this is still smooth evolution, the set of roots still comes back to itself, but what they're doing in between may be not super trivial. If this is what you get for, say, the blue loop, and by the way, this kind of object is called a braid. If this is the braid that you get for the green loop, which is little, and the bigger loop of the blue one gives you this braid, some other very much different loop like this red one may cause your eigenvalues to vary in a different way. This is a different braid. You can see the crossings are different. Okay. And so this is sort of the first point that I want to make. Just generically, because of this basic structure, any loop that you consider in this space of control parameters produces a braid of the eigenvalues. Maybe it's a real boring one, maybe it's less boring or whatever, but this is what these things are. So at this point, one question to say is, well, wait a minute, this braid is topologically distinct from this one, which is topologically distinct from that one. But these loops all look topologically not distinct. Like, I can smoothly deform this red loop into this blue loop, but somehow that would do something very dramatic to the braids. So in order to understand what is the connection between the topology of these loops, of a loop here, and the braid that it produces, let me use PowerPoint to illustrate what would happen if I just sort of force this red loop to gradually smush into the shape of the blue loop. And I will show you what happens to the braids as I do that. So this one will be animated here. So what I'm imagining doing is just smoothly deforming this red loop until it becomes the blue loop, and correspondingly smoothly deforming the trajectories of these roots until it goes from the original red one to the blue one. And you can see that what happens is that in order to go from this one to in order to go from this one to this one, what has to happen is that two of those strands have to get pushed through each other to become a new, topologically new kind of braid. And what that means, that's a very special moment when they get pushed through each other. At that point, the strands are such that two eigenvalues have become degenerate. That's what it means to push these guys together. So it means that in control space, smushing this red loop into this blue loop must have encountered a degeneracy somewhere in between the two. Okay, so strands have to get forced through each other, which is equivalent to saying that the loop must have been pushed through some kind of degenerate point. So what that says is that there's a point here of degeneracy between the eigenvalues. And somehow it's the presence of such a degeneracy that makes this red loop topologically distinct from the blue loop. This isn't obviously the full story because a point by itself can't topologically distinguish these loops. The loop could just scooch around that point. So it must be that the degeneracy is some kind of more extended object, which in fact it has to be because degeneracy is exactly one complex equality. Some eigenvalue is equal to some other eigenvalue. That's two real equalities. And so it's going to restrict you to a space that is 2 dimensions less than the full space. So in the cartoon in which this is a three-dimensional space, degeneracies must be one-dimensional structures. And one-dimensional structures are capable of making loops topologically distinct from each other. Okay, so that's the main story that I wanted to tell you. And again, if the red loop produces this kind of braid, and the blue loop produces this kind, and the green loop produces this kind, then there must be some kind of string of degeneracies that separates these two and another curve that separates these two. So generically, this is the kind of structure that exists in these systems. And what we can say robustly is that every loop that avoids these degeneracies produces a braid of eigenvalues. And more specifically, if you have two loops that are topologically equivalent with respect to the degeneracies, they will make topologically equivalent braids. Okay. I should say, like, I'm very happy to take questions in the course of the talk. So if there's, yeah.
Yeah, where parameter matrix, there's only an eigenvalue.
Yeah. Yeah, so this is a story in which we are sort of not caring anymore about the eigenvectors. So this is only a story about spectra and eigenvalues. And I have, for this entire talk, I'm not going to care what the modes look like. I'm only going to wonder about their resonance frequencies. Yeah.
Particles and terms of grading.
What?
Terms of grading two particles.
What's a particle? Yeah, sure. I drew 4 because it makes a more exciting cartoon. Okay, so I'm coming to that. That's next. Okay, so this is the cartoon, but it's nothing more than that. So in order to get a more precise picture of what the degeneracies shapes actually are and what sort of loops there are that enclose these degeneracies in various ways, I would like to sort of flesh out this story by telling you sort of what kinds of topologically distinct loops are there? How many different flavors? And this is a very famous concept in some areas. The catalog of all topologically distinct types of loops of a space is a way of characterizing its shape. It's sort of a way of characterizing the holes in a space. Okay? If a space has holes, I can draw loops around them that can't be collapsed into each other. And this notion is called the fundamental group of the space. I'll tell you why it's a group in a minute, but as just sort of a picture, let me just give you some illustrations. R3, the space in which we live, every loop, how many kind of topologically distinct kinds of loops are there? Just one. Every single loop can just be shrunk down to a point. There are no holes in our space to impede that. Okay? So this is the trivial group with just one element. Surface of a sphere, which in some sense is actually the world we live in, right? This looks more interesting, but nope. Actually, every loop on the sphere can be shrunk down to a point. So a sphere is different than Euclidean space, but in this regard, it's the same. There's only one kind of loop, the boring kind. Here's a space in which that is not the case. This is a space with a hole. And one way that I know that is that I can pick a starting point and draw a loop like this blue one that runs around clockwise, or one like this red one that runs around counterclockwise, and I cannot deform one into the other. Okay? So in this geometry, in this space, each loop is characterized by an integer, the signed winding number, if you like. Okay? So that's so here there's only one kind of loop. Here there's, countably infinite types of loop. The reason that this structure is a group and not, say, just a set is that in order to characterize these holes, I need to tell you one more thing, which is what happens when I take two loops, like maybe these two, and consider the loop that is just the concatenation of those two loops. That's still a loop. In this particular case, so what I imagine is I do sort of first the blue loop, and then I do the red loop. And I keep the starting and stopping point fixed, but everything else I'm free to deform. And you notice that I can shrink it back to 0. So this tells you that the loop that is gotten by concatenating +1 with -1 is topologically the same as loop 0. This is not an accident. In fact, the group of this space is the integers with addition. If you concatenate two loops, that is just the same as adding their winding number. That's true in this space. It's not generically true. So this slightly more exotic space with two holes, A and B, I could imagine this red loop B and this blue loop A. And if I consider the loop that is gotten by doing first A and then B, I cannot smoothly deform that into the loop that is gotten by doing first B and then A. I'll let you puzzle that out with your imagination, but it is true. They can't be smoothly deformed into each other. So in this geometry, the basic notion of going around something is a non-commutative notion. Another way of saying it is that the topology of this space has a fundamental group that's not abelian. And the reason that I've dragged you through this long aside on whatever like topology is that this is exactly what harmonic oscillators do. And it's for more than two harmonic oscillators that you get something like this. Okay, so why is that? Let's see, this is, okay, let me just sort of skip through this. So, so in what sense is this story of tuning oscillators like that? If I have two oscillators, I have a, here's a characteristic polynomial for a 2 by 2 traceless matrix. There's only, this will be your characteristic polynomial. There's one parameter z. And if I want to know, so when I tune it, I have exactly two knobs. So these polynomials live in a two-dimensional space, as advertised before. Here's that two-dimensional space, the real and imaginary part of this one parameter. As I said, what we're interested in is what's the space of this shape after I remove all the degeneracies. This space only has a degeneracy when z is 0. That's the only way for the two roots of this equation to be the same. So here's that degeneracy. And as we discussed generally, the space has two dimensions, and the subspace of degeneracies has two fewer dimensions than that. In this case, just a point. So this is now the space of non-degenerate spectra of two-mode systems. And what that means in terms of our story of braids and the like is that if I start at this point, I have two eigenvalues. And if I go around this red loop, those eigenvalues will vary in some smooth way and then come back to themselves. But if I was to go around this bigger control loop, blue, that actually encloses the origin and so is topologically distinct from the red one, my eigenvalues would trace out a braid like that, where they end up swapping. But the interesting thing is what they're doing in between. Okay. And so this is, again, a plane with a hole in it. Its fundamental group is just the integers. You do a loop. It's associated with an integer. You put two loops together. You just add those integers together. End of story. This is the sort of no interesting topology. This is, okay, and so here it is quickly summarized. The full space is the plane. The non-degenerate space is the plane minus the origin. The degeneracies are at the origin. The fundamental group is the group, a braid group for two strands, and here's a little picture of that space. Very boring. Okay, n equals 3, what happens? Again, the characteristic polynomial for an arbitrary traceless 3 by 3 matrix is here. X and y are any complex numbers you want. So apparently, these polynomials live in a 4-dimensional space, given by these two complex numbers. And that means I expect my space of degeneracies to be 2 dimensions less, some kind of 2D surface in this 4D space. I'm going to draw that for you. Okay. Maybe that sounds daunting, but here it is. So this is the 4-dimensional space, if you'll sort of humor me, pretending that this is 4 dimensions, of all such polynomials. The only way to make this polynomial have 3 degenerate roots, like all 3 roots are the same, is if x and y are 0. And then I say, hey, lambda cubed equals 0, 3 roots of 0. So there's only one point of triple degeneracy here. And since I know there have to be a full 2-dimensional space of degeneracies, everything left is the double degeneracies, the twofold ones. So where do they lie in this space? Wonderful thing that I got to learn about is every polynomial has another polynomial called its discriminant. And so it turns out if you have a polynomial like this and you say, hey, for what x and y do I get degenerate roots? It's just the roots of another polynomial called its discriminant. So it's a quote unquote well-known fact that if this x and this y stand in this relationship to each other, this polynomial will have degenerate roots. So all I have to do is to figure out where in this space does this equality hold. Can't be that hard, and it's actually not. Though it proceeds more nicely if you take these two complex numbers and represent them as in polar form. And I'm actually going to walk you through this because it's only like 2 steps and you get an awesome picture at the end. So I don't want you to think there's like some magic that happens here. So in order to figure out where on this space does this equation hold, let me start by restricting myself to the surface of maybe a unit sphere or just a sphere of arbitrary radius. That's because on the sphere, the magnitudes of these two complex numbers have a fixed relationship to each other. That removes one variable. And then between that constraint of being on the sphere and this constraint, that fixed the magnitudes r and rho, which means that for my two unknown complex numbers, the only thing that's still unknown is their phase angles, theta and phi. So I've now reduced the problem to 2 angles, theta and phi, which can each run from 0 to 2 pi. So that means I'm left with this space that is the surface of a torus. And I just want to know where on this torus does this equality hold. So here's the torus, which is some subpart of this 3-dimensional surface. And basically, if I'm going to take a complex number and cube it and another complex number and square it, their phase angles need to be 3 and 2 times each other. And this happens exactly on what's known as the 3-2 trefoil knot, which is shown here. So you go around the trefoil 3 times this way while going around it twice this way. So that's the solution of this equation. And so what it means then is that on the surface of any hypersphere in this space, I will have twofold degeneracies that form a trefoil knot in that space. And there's nothing special about working on this hypersphere. If I pick a hypersphere with smaller radius, that doesn't matter, tell the exact same story. There'll be another trefoil knot and another trefoil knot and another trefoil knot. And the 2-dimensional surface is sort of the sheet that's gotten by extruding a knot down to this triple degeneracy down to the point here. So this is a shape that is known as the cone of the trefoil knot. It's just a 2D surface that you can't embed in 3 dimensions, but you can sort of picture it. You slice it anywhere and you get a trefoil knot. Okay, and it just follows from this little bit of algebra. So physical consequences. Again, I'm not here to tell you about math for its own sake. Physical consequences say, okay, if you have a 3-oscillator system, 3-mode system, and you vary its parameters around some kind of a loop, your eigenvalues will trace out a braid of 3 strands, and which braid in particular will be determined by how did that loop snake through this trefoil knot of degeneracies. Did it do it like the black one or the blue one or the red one? Each one of these will give a topologically distinct braid of eigenvalues. So again, here's the picture. The 2-dimensional case was rather simple. Here's the 3-dimensional case, the full space and the degenerate subspace. No matter how much time you gave me, I cannot tell you what happens for n equals 4, 5, 6, etc. Don't have any pictures for that. But I do know that all the features that are in these higher dimensional structures are already present here. The degeneracies are some kind of knotted structure. Loops around them form a non-abelian group. Okay. So again, as math, this has been understood for at least 100 years. It is totally uncontroversial. We don't have to go do an experiment to check if the mathematicians got it right. They got it right. But look, if someone takes, like coupled oscillators are one of the world's most ubiquitous physical systems, supposedly very well understood. And if it turns out that there's this like very rich, powerful, elegant mathematical structure in them, which has been at least underappreciated up to this point, it would be nice at least just to measure it and see it at least once. Okay, so that's what we'll go ahead and do. So where can I find a system of 3 harmonic oscillators, 3 coupled oscillators that I can tune? Well, here's one. Here's another. It's a wine glass, and I just pick 3 of its normal modes and ignore the others. Here's another one, which you might find in various demo classes. All of these would work. Every single one of these has a trefoil knot of degeneracies in the space of its tuning parameters, these tuning pegs up here, okay? Without exception. So if you were to take one of them and tune 4 parameters, say the springs and the damping coefficients, and measure their resonance frequencies as a function of those parameters, and say, where do I find that 2 of these are equal to each other? They would lie on this cone of trefoil knots. In practice, we don't do it with wine glasses or Davy 504's 3-stringed bass. we have these nice little silicon nitride membranes, which are just drum heads. And at this point, I start to feel bad because now I have to describe to you this clunky experiment, none of which is particularly relevant to the story that I just told. So let me just say, we have some three-mode system. It really doesn't even matter what it is with appropriate tuning parameters. As it happens, it's three drumhead modes of this little object. Turns out that tuning parameters that are really nice are gotten by putting it inside of a high-finesse optical cavity and filling that cavity with laser light. The radiation pressure does a really nice job of stiffening and softening and dampening and anti-dampening and coupling and decoupling these modes in a nicely tunable way. It's just a convenient way of realizing any of those cartoons. In practice, it turns out that if you send in 3 different laser tones into this cavity, you get 4 nice linearly independent control knobs from their 3 powers, 1, 2, 3, and then just you take the 3 frequencies and detune them all together. That's your 4th knob. It just turns out that this enters into these oscillators in a linearly independent fashion. The actual experiment, for various reasons, was super complicated. That's history. Doesn't really matter for what I'm going to tell you about. All we do is we take this little membrane and we send in 3 laser beams with maybe these 3 powers and this detuning relative to the cavity resonance. And then we buzz the membrane and sweep the frequency of that buzz and measure its complex response on a lock-in. Okay? And so you see a resonance that looks like this for the 3 different resonances, and you fit it to the sum of 3 complex Lorentzians. It fits really well. What we get out of that are the 3 roots of the characteristic polynomials, the 3 eigenvalues, complex eigenvalues. You can think of the real part as being the center frequencies of each resonance and the imaginary part as being their width. And then we're just going to do that as a function of these laser parameters and ask how these eigenfrequencies move around in the complex plane. Okay, I'll skip this story. First, this is sort of just about convincing ourselves that they're really linearly independent. This is the story I want to tell you about, because it is a 4-dimensional space, right? That's where these trefoil knots live. And so I'm going to, again, draw you a 4-dimensional space in a pretty nice way. This is what we think of. And again, the assertion is that on the surface of some kind of cube-like shape, on that hypersurface, the twofold degeneracies will be a trefoil knot. I can draw this for you pretty faithfully. And the analogy is a more or less familiar one. If you have a 2-dimensional friend, flat friend, and you want to describe to them the surface of a box, you can say, well, look, I'm going to take that box, I'm going to unfold it into what's called the net of 6 squares and lay that in a plane. Your 2-dimensional friend is like, well, I can picture that. 6 squares laid out this way. Like your 3rd dimension is just like a bunch of hooey. That's not exotic. Then you say, okay, wait a minute. You just have to remember that the way that those squares are connected can't really be represented here. The squares are connected in this funny way, and then your 2-dimensional friend is like, okay, that's hard for me to picture, but I'll accept your story. You can do the exact same thing with the surface of a hypercube. It's a surface in 4 dimensions, which means it is itself 3 dimensions, which consists of 8 cubes, which are linked together in this way. That's not hard to picture. You just have to remember that, let's see, how would I say it? That like the faces of these 2 cubes are actually glued together, as are these faces, as are these faces, as are these faces. And when you draw that out, it is just each one of these cubes. The central one is the center here. The 6 faces around it are the 6 faces of this tesseract-y thing. And then one of those cubes gets stretched out to infinity. This is a stereographic projection, basically. And so what we do in our experiment is we actually take data as a function of these 4 knobs, filling out this 3-dimensional surface of the 4-dimensional space. And we plot that by doing the following. We take data by rastering our three parameters through one of these cubes, let's say, while fixing the 4th parameter, and then rastering them through this cube and this cube and this cube until all the data is stored in the computer. And then so if you like, we've rastered 3 parameters through this cube and 3 parameters through this cube while fixing one of the others, collect a lot of data in each of these cubes. Then we remember how they're supposed to be stitched together, all the data in these cubes. And then what I'm going to show you is just sticking them together to make the net and then sort of smooshing them until they're in this shape. And that's where all of our data lives, in this space. And this is a nice way of doing it because this essentially linear mapping lets me really put dimensionful units. Like this axis really is the power of laser beam 2, and this one is really the power of laser beam 1. So I can show data in a pretty honest way this way. In practice, the way that we take data is we don't have quite enough patience to just raster densely through that three-dimensional space. So we pick a lot of sort of two-dimensional sheets and raster around in them. And so at each point, what we do is we measure the eigenvalue spectrum, and we combine those eigenvalues into what's called, actually, our old friend, the polynomial discriminant. This is a combination of the complex eigenvalues that vanishes when there's a degeneracy, and it preserves the complex character, and it has a phase winding also around there. So this is the argument, the complex phase of this measured quantity, and its magnitude. So this looks like a 0. This looks like a phase winding. We didn't just want to pick the features we wanted to see, though. So we turned an image recognition algorithm loose on this to identify minima and phase windings. That required a bit of smoothing of the data, which is shown here. But we can also compare it to ab initio, just calculations of the optomechanical physics, the radiation pressure physics, and it agrees very nicely. So long story short, in each one of these sheets, we have something like this, and our algorithm maybe finds a degeneracy, or maybe finds 2, or maybe it doesn't find any. And then we just put those where we find them. So I'll now show you where all the degeneracies turned up. And those are these points here. And it might not be obvious from this view, but once I start to rotate it, you can see that these do indeed trace out a trefoil knot. The color that distinguishes them is not all twofold degeneracies are the same. There's an angle, which says in the complex plane, the axis that they form is oriented how in the complex plane. And that's encoded here as that color. And so it really lets us say, yeah, even though these degeneracies pass close to these, we know that their phase angle is super different. And so they are, in fact, distinct. This is the same data, not using our kind of experimentalists projection, but a more conventional dimensionless stereographic projection. And the solid line is just what you calculate for the degeneracies based on our knowledge of the microscopic device itself. Okay, so this is the first prediction, that the twofold degeneracies live on a trefoil knot. So here's that data again, and the fitted, sort of best fit knot through it. The other thing that I told you about, though, was that the eigenvalues will trace out braids determined by how your control loop passes around this knot. And we can already do that with the data we have, because we took eigenvalue spectra, not quite densely, but almost densely through this cube. So I'm just going to show you the eigenvalue spectrum for 20 points that we happen to take along this green curve here. So here's data points 0 through 20, each one shown as 3 points in the complex plane. Here they are. And here's what the theory predicts. This is a very boring braid. Well, this is a very boring loop. If I just take the data points that happen to lie on this red loop here, which encloses one arm of the knot, the eigenvalues do this as we move around the 60 points or so on the knot. If I take, again, this is just in software, if I just pick out the data that we happen to collect along this blue loop, the eigenvalues trace out a topologically distinct braid. And this is not like some delicate feature of the data. This is super robust. So you can just go into the data and say, hey, draw me this crazy loop, which goes around certain lobes of the knot, and you get this braid of eigenvalues, or this one, you get this, or this one, you get this. So there really is very robustly this correspondence between the topology of the braid, in the sense of how does it wind through this trefoil knot, sorry, the topology of this braid in terms of the topology of how the loop winds around through the knot of degeneracies. Yeah. Of what? An analog calculator of what? Yeah, but I would be hard pressed to sell you this calculator for very much. Yeah. Okay, so the very last thing that I will tell you about has to do with the non-commutativity of these loops. So this is, again, our degeneracy data, and I'm going to show you eigenvalue spectra collected from the starting black point here around the red loop. And then I'm going to show you the data collected around the blue loop, which starts from the same point, and I just stitch them together. If I take that exact same data, but stitch it together, first the blue and then the red, these are not the same braid. Like this root here let's see, let's take this one that's out front. It gets mapped over to the leftmost one, and here gets mapped over to the rightmost one, even though it's exactly the same data, just doing the operation in two different orders. Okay, so that's really everything that I was going to tell you. The conclusions, again, there's this like super well-known math. If you were to explain this to a mathematician, they would say, yeah, we learned this in undergraduate algebraic geometry or whatever, a class I never even heard of until I was very confused by all this and went and asked my theory colleagues. Anyway, there's this nice correspondence between this very elegant story and one of our most familiar building blocks of physics in both theory and experiment, which is just coupled oscillators. And it has the interesting consequence that for 3 modes and more, there's interesting topology. And you can really actually see this in real data. So again, maybe just the very last thing I would say is none of this was actually about time evolution. This was literally just the eigenvalues of matrices. Like we didn't even think about this equation here. So what we've been working on is what happens if you try to make use of this structure in real time. Like you prepare an excitation in one of these modes, and then while it's excited and ringing, in real time, you go around one of these loops. What happens to the energy? We're still puzzling that out, and hope to be able to tell you about that at some point in the future, thanks to these people's hard work. So again, thanks to these folks and our funding agency, and thank you very much for listening.
Start with you, Bill. Yeah.
So I know this is not about quantum or quantum. I just want to, if someone decides that the eigenvalue, points of eigenvalue that one certain stuff, they know, say, if I do this loop, it's going to take one state, so that one state to say state B, take state C to state B. So is this what people mean when they say they work?
No, not really. And yeah, I've asked that question a million times, and this is supernatural. So there's some similar math involved, but it is not like the physics is super different, and this is not a quantum computer. The closest analogy, though, that I could ask, that I think that would be to that, would be the statement, suppose that I could prepare a state in, I could excite this mode, I could put some energy in there, and adiabatically transport the system. And if the adiabatic theorem applied, which it doesn't, the state might evolve from this state to that other one. That's the same state. So like it might or might not swap or permute in an interesting way. The thing that would be really cool is there's any signature of the evolution upon arriving here, like the total accumulated phase that is uniquely associated with the braid that was traced out. That would be a little bit closer to the anionic quantum computing braiding story. And we're super curious as to whether or not that plays out in the classical mechanics of these systems, but I just don't know.
An online question?
Hello, this is a question from online.
Sure.
If the measurement has not matched your expectations, would this have tested any aspect of quantum mechanics or other more specific physical theories?
Short answer is no. So just as a reminder, there was no quantum mechanics here whatsoever. This was all classical mechanics, all F equals ma. If we had sort of learned this math and then done the experiment and not seen it, the math is right. So what we would have concluded is that our experimental apparatus was not in close correspondence with the mathematical model. I think that's what we would have taken away.
Let's go there. Yeah.
So we've been talking about mostly the Ferber polynomial. I guess it would make sense intuitively that there would be sheets and also sheets of like third degree degeneracies, and then also loops of third degree degeneracies and then sheets of second degree degeneracies, and then also like the one fourth degree degeneracy right at the center again. Is there any fun interaction that you observe between like the sheets and the loops in entire dimensions?
We've only looked at these three-dimensional case, and in principle, you know, the twofold degeneracies are a sheet. It's only when you take a slice of the space that you see a trefoil knot. We also did not have enough patience to take that data, like, oh, then like trefoil knots and steps and parameter and another one. That was just sort of beyond what we could do. But really, that doesn't matter because so this is all a statement about what happens when you encircle something. And the notion of encircling has to do with codimension 2. If you live in 47 dimensions and you claim you have encircled something, that thing had better be 45 dimensions. That's why if I have a point in 3D space, I can't tell you whether I encircled it or not. So this is a system with 4 dimensions. There's an interesting structure that's 2 dimensions. It's natural to ask what happens when I draw loops around it. There are higher dimensional analogs of this. There's the pi2 group, which is sort of what happens if I draw a plastic bag around some structure, things like that. I don't know what consequences that has for this kind of story.
In the diagram of braids passing through each other, which kind of corresponded to the higher dimensional loops passing through degeneracy, you mentioned that they said pass through each other, but in the animation, it kind of looked like they were almost splicing and then reconnecting with each other, like almost like starting and ending at different final.
Yeah, so I should probably have Mathematica do this properly. That is literally just PowerPoint's transition.
Oh, okay. I was going to ask, like mathematically different, like braids just passing through each other versus like splicing and reconnecting with other braids.
No, it's really, it would look like pop.
Okay.
That's all. Yeah. Sorry. So yeah. Okay. That's just PowerPoint transition. Yeah.
Good. Yeah.
So they have to take successive modes at some time. So these are
Any 3 modes. So again, like if you have, all you have to be able to do is to tune them. So in the space of their tuning parameters, you do need to be able to reach somewhere where actually they start to become degenerate. Yeah.
And that was, I think, related to what you asked. So when you encounter degeneracy points, you have to worry about linearity.
The system is totally linear. And the only place it could be not, so like this is just like a drum head vibrating. And we are just careful not to shake it too much. So we're measuring its response to a little tickle such that the amplitude of motion is always small enough that it's a harmonic oscillator. And being degenerate or not does not change that.
Jack, one final question, maybe.
Okay.
Can you always engineer the parameters of 3 oscillators to produce any knot you want, or are certain knots physically forbidden?
This is the only knot you will get for 3 oscillators. This is the knot. This is the locus of double degeneracies within the space of 3rd order polynomials. That's all you got.
No way to get any other.
I'm open to
space other than
suggestions.
knots. Okay. All right. Please join me in thanking Jack once
Thank you.
again for a fantastic
Thank you
talk.
very much.